Okay, welcome to the first blood gas of the week case. We're going to jump straight to interpretation in this video, so if you need a refresher on the normal values or how to interpret the blood gas, go check out the how-to videos first, then come back to this video. Alright, let's get started. We were presented with an 11-year-old cat who's really quite sick. He has a 2 to 3 week history of progressive anorexia, vomiting, regurgitation, and weight loss. Today he's conscious, but not interacting with the owner, and over the last few days the owner's noticed a progressive bloating of the abdomen. On the initial assessment of the cat, he's sitting in a sternal position with his neck ventriflexed. He's cold, bradycardic, tachypnic. He has a prolonged CRT, and his blood pressure on the Doppler is 92 millimeters of mercury. While we were getting blood and placing an IV catheter, he vomited a large volume of green fluid all over us, and while we finished cleaning that up, his blood work came back. And this is what we've got. There's quite a few abnormalities there, but let's focus on the acid-base components right now. If you haven't already interpreted the results, hit pause, write down your interpretation, then hit play again. Alright. The first step in interpreting the blood gas is to determine what type of sample we have. Is it arterial or venous? This is a venous sample, so we know we aren't going to be looking at an oxygenation status, so we can move straight on to the acid-base interpretation. So step 1 is to assess the pH of the blood. This patient's pH is 7.55. It's really high, which means the patient has an alkalemia. Next, we need to decide if the respiratory or metabolic component is causing the alkalemia. The two ways to get an alkalemia are to have a low CO2 or a high bicarbonate. Our patient has a really high CO2. That doesn't match because that's a respiratory acidosis. So that's not the cause of our patient's alkalemia. So we look at the bicarbonate, and we see he has a very high bicarbonate, which means a metabolic alkalosis. Since the pH is alkalemia, and the high bicarbonate means a metabolic alkalosis, the patient's primary problem is a metabolic alkalosis. The next step is to determine if the compensation is occurring. If it was, we would expect the patient to, with a metabolic alkalosis, to try to compensate by having a respiratory acidosis. And indeed, our patient is cooperating and has a very high PCO2. So for those who prefer the tic-tac-toe method, we're going to look at the pH, and we see that it's 7.55, which is high, and therefore that's basic. The CO2 is 71, which is really high, which is an acidifying process, so acid. And a high bicarbonate is going to go over under the basic column. The pH and the bicarbonate line up in the same column, so we have a metabolic alkalosis as the primary problem and a respiratory compensation with a respiratory acidosis. So it looks like our patient is a compensated metabolic alkalosis. We can stop here, but if you want to take your analysis one step further, we could check some math and confirm that the change in the PCO2 is just a compensatory change. Since some of our really sick patients can have more than one problem that can cause changes in the blood gas, we can use mathematic formulas to determine if the changes that look like compensation really are compensation, or if we need to go looking for secondary problems. When the primary problem is a metabolic alkalosis like our patient has, the formula says that for every 1 point increase in the bicarbonate above normal, the PCO2 should increase by 0.7 points. So let's take a look at our patient. Step 1 is to see how much the bicarbonate has changed from normal. A normal bicarbonate is about 20, so we're going to subtract 20 from our patient's measured bicarbonate of 58.9. That gives us a change of 38.9 points. So for every 1 point change in the bicarbonate, the CO2 should change by 0.7. So we're going to take that 38.9 multiplied by 0.7, which gives us 27. So we think our CO2 should go up by about 27 points in response to the abnormal bicarbonate. A normal PCO2 is about 40, so we're going to take 27 and add 40 to that and get 67. This means we would expect the CO2 to be about 67 if the change in CO2 is just compensation for the metabolic alkalosis. But we know that there is actually a range for normal CO2 and bicarbonate in our patients. Not everyone's normal bicarbonate is exactly 20, and not everyone's normal CO2 is exactly 40. So we need to use a range. And as a general rule, we're going to use a range of plus or minus 4 on either side of the calculated value. So our calculated value was 67. 67 minus 4 is 63. 67 plus 4 is 71. So if the patient's measured CO2 falls into this range of 63 to 71, we can say that the change in the CO2 is likely all due to compensation. Our patient's CO2 is 71. It falls into our range, so his change in CO2 is probably compensation for his severe metabolic alkalosis. There's probably not something else making his CO2 go higher. So our final acid-base diagnosis today is a compensated metabolic alkalosis. Thanks for checking out the video. We'll do this again next week. Until then, cheers.